I'm Terry Voigt, so I'm a senior applications engineer here at Toshiba International Corporation. And I will be your presenter today. So I'm going to talk a little bit about harmonics and a few other just drive offerings. So with me as well, so my co-host is Josh Austin. So he will be answering questions throughout the email or the presentation as well, and then bring up any unanswered questions at the end of the presentation too. So let's go ahead and get started. So today, like I mentioned, we're going to learn a little bit about harmonics. And then an introduction to some newer technology, so new VFD technology, so silicon carbide active front end technology. So to start with, we're just going to talk a little bit about harmonics, right? So what are harmonics? Where do harmonics come from? So essentially, harmonics are a bunch of little waveforms. So you have the first fundamental waveform, as you see in the presentation. Then you have little harmonics too. So 5th, 7th, 11th, 13th. Those are examples. They go up through a very, very high number. So high order of harmonics. It's maybe also considered like a harmonic spectrum is another fancy word that gets used in this topic as well. But essentially, the overall waveform, uh, everything gets added up, and then we get a final waveform. So here's kind of another graphic or another illustration where we have the fundamental. So that's the this blue line right here. So that's the initial one, and then we have smaller ones. So that's the kind of the magenta, the yellow, the pink. Those are all of the smaller harmonics, and then those get added up into, in this case, that white line. So that white is the resulting waveform, which doesn't really look like anything like the fundamental in this example, right? So you can kind of see the impact that harmonics can have on a system. Well, in the real world, so here's an example of a scope shot that has some pretty drastic harmonics on it, right? So this is just a voltage waveform that was captured that looks like a waveform. It does not look clean by any means, right? So this is definitely being affected by harmonics in this case. So voltage harmonics are being affected in this picture. Similarly, here's another one. Here's just more amperage values actually. So here's just a skewed amperage value. So you can see harmonics are negatively affecting this waveform as well. So it looks like a sine wave, but it's a little modified, we'll say. So what are some sources? So what creates harmonics? So ultimately, it's anything that kind of converts AC to DC. So like copiers, they can convert AC power to DC power. Fax machines, computers. We'll talk a lot about AC motor drives. So they're a big influence of harmonics in industrial power systems, but also like lighting systems. So like LED lightings can affect that, and then also like fluorescent lighting, and then UPSs as well. So what are some issues that result from harmonics? So excessive heating, either in transformers or in different types of equipment. Uh, Excess harmonics can result in heating, just torque pulsations, just kind of just strange faults or strange errors in a lot of metering equipment. So either like kilowatt hour metering equipment or like sensitive like milliamp measuring devices. That can all be some effects of harmonic issues. So a commonly asked question that we get are, do harmonics only flow downstream? That is a good question, and ultimately the answer is no. They can flow downstream and also upstream. So in general, we talk about harmonics on the front end or the industrial power supply of systems, but they can also affect the downstream end of a drive in this case. So that would be like the motors or like the pumps, like the rotating equipment, bearings, that type of thing. So we can definitely talk about harmonics on both ends of the spectrum. So both upstream equipment and also downstream equipment. All right, let's talk a little bit about the IEEE 519 standard. So they kind of specify the rules, right? So how much harmonics are detrimental, and that type of thing. So how much are allowed, and then how much can affect other customers. So a few things we want to keep in mind is really there's two types of distortion. So with power, right? So power consists of both voltage and current. So the voltage distortion, the specific limits for that are 5% for individual voltage harmonics, and then 8% for the THD or total harmonic distortion. So that's kind of the overall resulting harmonics from everything in the system. For a current distortion or amperage distortion, there's a lot more flexibility, or there's a lot more ranges. Instead of just a 5 and an 8 for voltage, there's a specific table, just because there's a lot of different variability, just system variances that can apply. So, and we'll look at that specific table here in a little bit. A few other common terms to keep in mind is the point of common coupling. So in specifications, sometimes the PCC can change. So sometimes it says, well, the PCC can be at the front of the drive terminals. IEEE actually technically defines it as the distribution, so the transformer of the user. So the user's transformer is really the PCC. So that way it encompasses the whole entire system, not just one individual component of a larger system. Another term to keep in mind is the ISC slash IL ratio, or short circuit ratio. So that's a few different amperage components. Basically, it's the short circuit current ratio divided by the maximum fundamental load current is ultimately what that is. And speaking of the maximum load current, that I sub L, ultimately that is the recommended, it's the average current over the maximum demand over a period of time. So normally 12 months is kind of what that is, what that ends up being. So the THD, so I mentioned that earlier. So what is THD? So here is the equation for it. So essentially it's the ratio, so two divided numbers. So the top number is the root sum square of the harmonic values, all added together, and then take the root mean square of that, and then divided that by the fundamental voltage. And then you get the overall VTHD type of calculation. So it's a summation divided by the fundamental voltage, basically. So here are some more additional voltage harmonic standards. So for low voltage systems, so 1,000 volts and below, that's where we get our individual component is 5%, and then the overall total harmonic distortion is 8%. For larger systems, so you see that 1 kV to 69 kV, the voltage recommendations get lower, 69 to 161 kV, or even lower, and then the 161 and above are even lower than that. So just depending on what realm of the voltage world you live in, these voltage distortion limits can change, right? So in general, in the low voltage world though, we look at 5% and 8%. All right, so current distortion. So it's a similar type of calculation for amperage. So we take the root sum square of the individual harmonic contents, and then divide them by the fundamental current. And then an additional or a new value is ITDD. So that's the dynamic distortion. So total demand distortion is what that value is. So, and ultimately it's the uh, same numerator, but the denominator changes a little bit. So that's the maximum demand current is what that turns into. So not necessarily the fundamental, but it's the demand. So what are you using, or what are you normally using for current? So here's that table that I talked about earlier. So like I mentioned, the distortion limits can vary, and ultimately it varies depending on your circuit current ratio. So that's that ISC divided by IL. So depending on that result, and it's really going to change depending on your system, whether your transformer is heavily loaded or lightly loaded. The size of the transformer changes that ratio as well. So depending on that number, then you will get your resulting individual harmonics limitation, and then also the overall TDD required, right? So depending on if your IC8 or your short circuit current ratio is very low, then you can get as minimum as 5% TDD required, up to 20% if it's high enough. Some people I've seen that require everything as 5%, no matter what. But you do see IEEE 519 does allow for a little higher harmonic content depending on your system. So just kind of, again, you can kind of look at this specification in a few different ways. All right, another commonly asked question is, where is IEEE 519 most commonly required? So, or another way to think about it is, where is it most applied, or where do we see it most common tied with? And essentially the two largest that I normally see this tied with is the HVAC industry. So commercial buildings, like hospitals, that type of thing, like where you have lots of VFDs in a large building. So VFDs are very commonly used to provide water throughout the building, and then also air, right? So air conditioning or heat throughout the building. So a lot of those are variable rate type applications. So during those applications, VFDs are used. So the the result of that is a lot of times VFDs have some negative harmonic effects, right? So HVAC is a big one, and the other one is the water and wastewater industry. And the reason why that is, so we have smaller pumps, like pump stations located throughout the country, or smaller areas. So IEEE 519 is important there because the voltage that they're consuming, or the power that they're consuming, is primarily on a VFD. So they have a large pump with a VFD on it, and that's the majority of the power they consume. So since that's the majority of the power they consume, then they need to abide by IEEE 519 more. So that's one of the reasons. Another one is, a lot of times they're located in residential areas. So the IEEE 519 is kind of protecting people from voltage that one customer uses to not affect other customers. So that's another area that I see IEEE 519 most commonly applied, is the water and wastewater industry. All right, so I mentioned drives create harmonics, but why? So what in a drive makes them create harmonics, or just in general, that's kind of what they do. I briefly mentioned it earlier. It's just AC to DC conversion, right? So a drive, so there's a topology or a component layout in the upper right-hand corner of the screen. So that's ultimately what the components that are in a drive. So the input converter, or the diode bridge, that is the first part that converts AC to DC. So the second part is a capacitor section, and then the output part is the IGBTs, right? So it's that first part, that AC to DC conversion, that's ultimately where the harmonics are being generated from. So just that conversion, so those diodes, they will block voltage in one direction, and then allow voltage in the forward biasing direction, right? So during that negative biasing, that's highly influencing the amperage, and then also the resulting voltage that comes into play as well. So that's ultimately why it's being generated, but which harmonics are being generated? So we have the formula on the screen as well. Ultimately, what you kind of got to remember is a 6-pulse drive. So that's really where 6 diodes are being used. Create harmonics starting at the 5th. So it's the pulse count -1. That's where volt or harmonics start being generated. So on a 6-pulse drive, we get 5, 7, 11, 13, 17, and so on. We can increase the pulse count, which then decreases harmonics, which we'll look at shortly too. Here's kind of a better look at the resulting harmonics. So we see the line voltage that's in the system. So the dotted line is the theoretical voltage that we want, and then the blue line is the line voltage. So that's the actual voltage that gets resulting after it's influenced by harmonics, right? So it looks a little different than a regular waveform. And actually the amperage is affected even worse. So we see the dotted line looks just like a sine wave, but that red line at the bottom does not look like a normal sine wave, I would say. So that's the resulting sine wave because of those diodes. So you can kind of see amperage flows just fine right away, but once we get to the negative cycle, it turns off or it stops, right? So, and it does that 2 cycles for every 1 amperage cycle is kind of what that looks like. So you can kind of see the resulting amperage values have a much higher effect than a voltage value. So, and here's a little bit more information on, like I said, that 6 pulse, 12 pulse, 18 pulse. So these are common pulse counts in a drive. So in a low voltage drive, we can normally we see a 6 pulse drive. That's the most common one that's on the market. Also, higher pulse drives, we can have a 12 pulse drive, 18 pulse drive. Those are more what we call a reduced or a low harmonic drive, would be 12 and 18 pulse for the low voltage spectrum. 24 pulse drives and actually 36 pulse drives can be used in more the medium voltage world, where the voltage is even more sensitive, essentially, because with bigger power, you have to pay even more attention to harmonics specifically. So the overall theoretical max harmonic distortion, you can kind of just get a visual representation here, just kind of comparing 6, 12, 18, and 24. So you see the normal VFD, or the most common, right? So 6 pulse, it generates a lot of harmonic content, unfortunately. So just depending on the whole mixture of the system, that might be recognizable in the total total harmonic distortion calculation, or it might not, right? So if you have 1,000 horsepower worth of power, but you're using a 1 horsepower drive, that's a 6 pulse drive, you're not really going to make a huge impact on the entire harmonic spectrum. But if you're using, a 900 horsepower drive and 1,000 horsepower total, you're definitely going to see some of those effects. So we have a kind of a quick poll. I don't have a way to do polls in this format, but if we can kind of think about this, so let's think about this question and answer it kind of on your own. So, what harmonic mitigation methods are you most familiar with? So I talked about a few, but on your own. So in general, what harmonic mitigation methods are you most familiar with? So options are reactors, so DC reactors, like inside of a drive, or you can do a 3% or 5% AC reactors. There's multi-pulse options, which I just talked about, right? So 12, 18, 36. There's also harmonic filters. So there's filters that can specifically be designed to either trap or mitigate the harmonics that get generated, or AFE drives or active front end drives. So those are the 4 most common ways to either mitigate or not produce harmonics. So hopefully we've all kind of answered this question in our head, but I will go ahead and talk through some of those. So some typical solutions, like I mentioned, it's a 6 pulse drive with either DC choke or AC line reactor. You can also pair a 6 pulse drive with a passive harmonic filter. So that's a 1-to-1. So basically one drive you have to pair with one harmonic filter, and that device traps harmonics. So it will kind of capture or prevent the harmonics from leaving the filter. So this is installed on the front end, so the power side of the drive. You can also have 12 or 18 pulse drives. So those need a specific transformer to be paired with the extra diodes, basically. So it will shift and then cancel out any of the harmonics that get generated. So those are 2 other options. and then also active front end drives. So I briefly mentioned that too. So those actually have IGBTs on the front end to only sample or only bring in the voltage when needed. So instead of like with a diode that just brings it in all the time and just blocks it when it's on the negative side, an active front end drive will just very, very fine-tunely sample the voltage and only bring in what's needed. So we'll talk about that a little later too. So here's an example of a 6-pulse drive. So we see the schematic on the screen. It's very similar to the one that I showed earlier, but you see the 6 diodes, right? That's the 6 pulses that we're working with, and then the back end, or the middle and the back end, are the same, right? If we compare that to a 6-pulse drive with a DC choke, we see in the middle, so between the diodes and the capacitor, there are a DC choke, in this case 2 DC chokes that are added to the circuit, or added to the schematic, right? So in the resulting effect, you see in the upper right-hand corner, so the model number VFAS1, so that's a previous version of a Toshiba drive. The updated VFAS3, those have a DC link reactor built into it. So, and you can see the resulting current between the two. So the reaction changes. So the overall peak amperage on the AS1 is much higher compared to the more averaged or lesser of the VFAS3, right? So you can see the effect of that DC link reactor that it has, just to lessen the influence uh, that current harmonic has. So we can further reduce harmonics with a line reactor, so either 3% or a 5% line reactor. So that gets placed before the drive exists. So a DC link reactor is technically inside the drive, or it has terminals to connect it in series, essentially, with the drive itself. With the 3% line reactor, it's attached to the front end, right? So it's attached in series between the power source and the drive itself. So that helps with reducing harmonics, similarly to a DC link reactor, but it also has an advantage of incoming transient protection. So any voltage spikes, stuff like that, or just voltage imbalances, the line reactor does a better job of protecting the drive than just a DC link reactor. The harmonic spectrum wise, depending on the sizing, a lot of times it's very similar though. But this can be added after the fact, where a DC link reactor a lot of times can't. So another example is a passive harmonic filter, right? So this again gets added to the front end of a drive, so it can be added in the field, or in our case, so you see the picture on the right. So this is a AS3 with the passive harmonic filter mounted in the cabinet on the right. So you see the magnetics, so the 2 reactors. So it's basically a big ACL on the front end, and then there's a tuning circuit which has a line reactor, and then at the bottom you see the capacitors. So ultimately, this is the device that I was talking about, the filter that traps the harmonics inside of the circuit. So it will absorb all of the harmonics that are being generated by the drive and prevents them from getting into the power system. So this is a passive harmonic filter solution. There are big benefits to it, so that it does a very, very good job of reducing harmonics, but you can kind of see the physical space that it needs is kind of large. It's quite large. Similarly, with a 18 pulse drive with an auto transformer, it honestly takes up more space than like a line reactor or other solutions, but they do a very good job of canceling harmonics. So in this case, this is our plus pack, and it does have an option to uh, with a 18 pulse front end, which we have the 6 diodes, just like regular, but we add an additional 12 diodes and then connect that to an auto transformer is what that device is called. So that auto transformer will transform the voltage that comes in, shifts it by 120 degrees, and then we have two other sets of voltages that we can rectify, and then we mix that with the regular DC bus and then now that's ultimately what creates our 18 pulse drive. So now our harmonics are being generated from the 17th harmonic and higher instead of the 5th and higher. So in generally too, it was mentioned in some earlier screens, the lower magnitude harmonics are generally higher. So the 5th and 7th, for example, are normally the two biggest harmonics that gets generated by a drive. So if we can cancel those out, plus the additional ones, the overall harmonic spectrum becomes much lower. So a big advantage. So, and the last example that I talked about earlier was an active front-end drive. So, and that's where the WC1 comes in. So the WC1 is a new product offering from Toshiba. It's an active front-end drive. So there's a lot of good things that we can talk about with the WC1. The first one, obviously, being lower harmonic, and it's a lower harmonic footprint, right? So that's one big benefit of it. And I'll talk about a few of the other big benefits that this drive has as well. So you can see some of them listed on the screen here. The most unique characteristic of the WC1 is it uses silicon carbide technology. So this isn't just a regular IGBT or just a MOSFET or a switch. It uses a silicon carbide um, transistor, basically. So the importance with that, or with silicon carbide, is a lot of the things that you see on the screen. So it has very high switching frequency, the temperature regulation, it can get a lot hotter basically. It can support much higher voltages, and the overall power loss is less on a percentage basis. So there's a lot of good things with silicon carbide transistors. There are some negatives though, so there are some downsides, which we have taken care of inside of the WC1, right? So the increased DVDT spikes, so ultimately there's a filter that we take care of those higher spikes, and there is also an increased EMI noise. So there's an EMI filter that's built into the WC1, so that way we can negate those two negatives that are on the right-hand side. Again, we just use a filter to counteract them. And just FYI too, so silicon carbide transistors, they're very commonly used in many different industries. The most common one is actually EVs. So EV vehicles will use a silicon carbide transistor, so very fast switching. So there's not a brand new technology, but it's brand new to the industrial market for sure. So a few other unique characteristics about the WC1, like I mentioned earlier, right? So it's an active front-end drive. So that rectifier section that uses what's called an SiC MOSFET. So it's not necessarily a transistor. It's a type of transistor, but it's not an IGBT. So it switches much faster. So we can get much better control. Talked about the low THDI. So the THDI component here can be as low as 5% up to the 100th harmonic. So that's extremely low harmonic regulation. So I mentioned earlier, so some engineering firms will say, I want everything 5% below, 5% or below. This drive by itself will allow that, will pass that. So that's on the front end. It has capacitors. So there are some active front-end drives that don't have capacitors in the market. They're called a matrix drive. They work very well. The added capacitance, though, adds some reliability to the system. So this has a capacitor and an inductor inside the regular inside the middle section, right? So it's very similar to a regular six pulse drive. And a very unique thing about the output of this one, so it has MOSFETs on the output, but it also has a sine wave filter. So, and it's bidirectional as well, which means that power can flow from right to left or left to right in this case. So the energy flow can be motoring, so the motor consumes the energy. It's also fully regenerative, so it can pass any regen that might happen onto the incoming waveform. And I mentioned too, so the silicon carbide is very fast switching, so it's an effective 210 kilohertz switching frequency, which just for example, on the AS3 that I showed earlier, the default carrier frequency on the small units so is 4 kilohertz. And it can be raised up to 16. So compare that to the 210 kilohertz effective. That's quite a big difference. It's like I said, it just switches very, very quickly. So talking about the reduced harmonics with the WC1, so the IEEE 519, they regulate up to the 50th order. There's nothing wrong with that. That's what their specification is designed around. And traditional AFE drives, they do create harmonics above the 50th. So that is one downside to using active front-end technology is sometimes the harmonics that they can create, since they do switch very, very quickly, and they switch now on the input, you can create higher harmonics than what's normally measured. So up to the 50th or above the 50th in this case. With the WC1, it does not have those super harmonics that are basically the harmonics from the 50th to the 100th waveform range. So that can help drastically with any kind of transformer potentially overheating or some transformers that may lead to or predetermined failure, basically. So this is one important characteristic of the WC1 that can help input power drastically. So I mentioned the reduced harmonics, right? So less than 5%. So this is a result of a case study that we did. So we put the WC1 into an application. And we measured the harmonics that were generated by the drive. And in this case, we actually had 3% or less, or right around 3% or less for the THDI actual measured in a real world situation. So this isn't just bench testing. This was actually measured in the real world, so in the field. So 3% or less. So extremely, extremely small harmonic content. I mentioned the output. So the output actually has a sine wave filter built into it too. So that has multiple benefits for the motor. So not only are we protecting the front end, right? So not only are we protecting the connected power, but we're also protecting the motor. So eliminating the IGBTs or the PWM waveform on the output can help protect a lot of things that drives normally just come with, right? So cooling is the first one. So since it's a sine wave output, the motor runs much, much cooler. It virtually eliminates any common mode voltage. So you can connect a common mode filter to the output of a drive. That type of filter is also built into the WC1. So you don't need an external filter. It has it built into the drive. And then ultimately, there are no restrictions on cable length or cable type. So you can run, the only thing you have to be aware of is voltage drop in this case. So essentially, like I mentioned, it has a sine wave filter, not a DVDT filter, a sine wave filter built into it. So you can run miles of cable if you want to, then you just have to calculate your voltage drop and then um, plan for that accordingly. So let's look at the actual voltage, and you can hear the difference too. So I don't have the ability to have you hear what this sounds like, but you can kind of imagine. I'm assuming we've all heard what a motor that is connected to a drive, what it sounds like. And the reason is the picture on the left. So that is a PWM waveform of an AS3 that's connected to a motor, right? That's pretty typical. I would say that looks like a very typical waveform at the motor when it's connected to a drive. And you can hear it. You can kind of hear that ringing or that singing that motors normally make. The reason why we can hear that is it's because of that the carrier frequency essentially. So the frequency that the drive uses to create that PWM waveform, that's what we're hearing. But in the case of the WC1, so that's the waveform on the right side. and that's the output voltage. So that's the voltage that's going to the motor from a drive, specifically from the WC1. So they're very, very different waveforms. And you can audibly hear when you hear this drive run, that's the first thing that you notice is you can't tell that the motor's running. You can hear the water running, you can hear the bearings spin, but normally you would hear the voltage inside the motor. With the WC1, you can't hear that. It is quite incredible. So here's some more graphs of the difference of the cooling, so the temperature comparison. So here's a different load profile, so 25, 50, 100%. The motor gets warmer as you obviously produce more amperage, but when you compare that to a regular PWM drive, the 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 decrease in temperature is noticeable, right? So you see the graphs on the right-hand side too. Every single time the PWM drive has higher temperature than the WC1. So this leads to longer motor life and potentially just less bearing issues, less motor or less load issues, stuff like that. So it can be a very, very big tool to help solve some issues in high temperature situations. So here's some more harmonic characteristics. So specifically the THDI on the input side. So the graph on the left kind of denotes the grid, and then the graph on the right denotes the motor. So the THDI in the motor characteristics, and you can see in each case, it's either the same or less. The WC1 compared to a different AFE drive. So a lot of times stuff gets talked about at 100% load, so full load, which is common. There's nothing wrong with that. But the less that you load a normal AFE drive, the worse harmonic performance it becomes, right? So you can kind of see that with the graph on the left. So the 100% loaded, very, very low harmonic content, but the less that it's loaded, ultimately the higher harmonic content it generates. On the right-hand side, so you have the THDI of the motor. That's the result of the sine wave filter that's built into it. We have very little, very, very little THDI, so current harmonics on the output, because we're sending out an actual sine wave form instead of a PWM waveform. So we can decrease the footprint. So I talked about earlier, so like with a harmonic filter, the footprint just becomes very large. With the WC1, it isn't really that much bigger than a regular AS3 if we're looking at from horsepower to horsepower. And we get a lot of extra components inside of it, right? So we talked about the magnetics. You can physically see the magnetics in like in that harmonic filter. How can we get a lot of filters, so essentially a sine wave filter on the input and a sine wave filter on the output, plus an EMI filter? How can we get all of those filters in such a small package? And the reason is the high switching frequency. So because the switching frequency is so high, that greatly reduces the size of the magnetic components that are needed inside the drive. So the actual switching frequency of the drive is 105 kilohertz. I mentioned earlier that the effective frequency is 210. The reason why we double the effective is because it has a stepped waveform. So the waveform on the output actually has multi-levels. So it's a multi-level output. So the effective frequency is double the actual carrier frequency. Another big benefit to using or these kind of components too is film capacitors are used. So instead of electrolytic capacitors inside of a normal VFD, they have a shelf life essentially, or need to be reconditioned after they sit idle, let's say about 2 years. It's best to connect power back up to the capacitors so they can kind of mix the oil solution, the electrolytic solution inside the capacitors. The WC1 uses a film type capacitor, so that means you don't need to do that. So the shelf life becomes much, much longer on a film type capacitor versus an electrolytic capacitor. Improved efficiency. So as you can see, we're taking a bunch of different components and putting them into one drive. So you see that graphic on the right. We just have the power supply, the WC1, and the motor. Overall, that becomes more efficient than a 6-pulse drive and a choke, and then adding a harmonic filter, and then adding an output filter, whether that be a DVDT filter, a sine wave filter to compare apple to apples in this case, along with um, the common mode choke as well. So if we add up all of the relative efficiencies of each device, on the left, we get 89 to 95% depending on the components that are used. Comparing that to the WC1, we're at 96% at the lowest end. So it's a improved efficiency overall. So you're just spending less energy to do the same thing. So a quick overview of what the WC1 looks like, what it has inside of it. The HMI is detachable. It can be remote mounted. There's control terminal blocks that can be remote mounted. The power terminal blocks are at the bottom left that you see there. The components or the PCBs are all conformally coded, so that complies with a lot of environmental standards. There's a replaceable battery used to save the real-time clock, USB ports, there's an HMI screen port, and then also 2 daisy-chained Ethernet ports as well. So that can be used with Ethernet IP and then also Modbus TCP IP. Here's a closer look at the actual terminals themselves. So we have relays, so those are full contact relays, an STO, so a safe torque off circuit. We have our analog outputs, our digital inputs, and some analog inputs as well. So very typical for a Toshiba drive. The same naming convention applies to all of those as well. So it should be very, very familiar to wire up an AS3 versus wiring up a WC1. For example, the F terminal runs forward. It runs forward in the AS3 and most of our other drives, and in the WC1, the F terminal will run the drive forward. Here's a look at the keypad. So just kind of a quick glance at that. The operating status, you can name the drive. You get the motor speed, either in frequency, that can also be changed to RPM as well. We get a monitor mode, so you can monitor the amperage, the voltage, and the frequency. There's different menus. There's a start button, a stop button, local remote control. There's also different statuses and times and different other monitor items as well. And as you can see, it's IP20, so NEMA 1 mount ready. You don't need any extra external kit. You just line up the mounting holes and attach it to a panel. Additionally, in the screen, we also are able to program the drive and monitor the drive using an app. So the app is available for both Android and iPhone. And it connects through Bluetooth. So you can pair the device, so it can also work with like a tablet. You pair the device to the drive itself. You can pre-program it and then send the program into the drive. You can either duplicate, very easily duplicated programming that way, or you can just for safekeeping do a similar type of configuration. So to kind of review all of the different applications for the WC1 where we see it fitting the best, clean input. So specifically what we're talking about here, low harmonics, right? So for the HVAC water wastewater world where harmonics are a big concern, the WC1 would be a great fit. Other applications, fully regenerative, so any type of fully regenerative application, clean output as well, right? So there's a sine wave filter built into it, so that reduces a lot of the motor issues, and then along with that, the enhanced motor life too. So that's the biggest benefits we see from the WC1. Thank you for joining me for the webinar today. So that's all the information that I have. There is a QR code that you can visit. You can visit our website. That's our phone number as well, so that will get you in touch with an application engineer from our group. You can also send us an email, so tic-service at toshiba.com. And that's all the information that I have. So do we have any questions? Maybe Josh answered all of them.
I see, not quite there. I'm not
There we
that
go.
great, but so there are some, I think, some people raising their hands. If you're able to, if you could go ahead and type your question in the chat, that way we can read the question to the whole audience.
Very good. Did you have any questions that we need to answer yet?
So, okay, we do have a couple going in. So regarding the WC1, there are a couple of questions relating to the release date or when they're going to be available. If you want to talk about that.
Yeah, depending on the horsepower range. So they'll be available in the next couple months towards the end of the year. So I think it's up through 30 horsepower is available or will be available first. And then we're expecting 60 horsepower by the end of the year.
Yeah, and of course, always you have your contact information registered with Toshiba. You'll be able to get mass email updates on when that's available.
Mhm.
Another question, Terry, is about the software connectivity. So I think you mentioned the mobile app that's on smartphones.
Mhm.
Um, do you want to talk about how, typically our other drives use ASD Pro on PC computers? And you want to talk about maybe the difference or compatibility in the future, possibly?
Correct. Yeah. There's absolutely right. So we have a P or an app that's available with the WC1. It will also have a embedded web server, so you can interact with the drive that way with a computer or a device. Uh, Regarding uh, the ASD Pro type connectivity, at the moment we're not expecting the WC1 to work with ASD Pro. That might change, or we might integrate that at a later time. But at the moment, or specifically on release, we're not planning on giving support with ASD Pro with the WC1 because it has the app and also the web server capability.
And then we have one question regarding temperature. So the temperature ratings that you covered in the presentation, was that in Fahrenheit or Celsius?
That would be Celsius. So and I think that was specifically listed on the first slide. So it should be up to 50 degrees C. And the temperature of the motor was in C2.
Okay. And then regarding IEEE 519, there's a question regarding how often do we see that being measured in the field? The particular person was asking about West Texas pump jack applications.
Gotcha. Often, not necessarily, no. Um, it does, it can become an issue. It normally gets measured when there are different issues. So when we see kind of different random issues occurring, then we'll say, well, this could be harmonics related because West Texas specifically, kind of my example earlier, right? So the majority of the power consumption is going to be VFD related, especially on kind of more remote situations, right? So that could be some high harmonic content that's happening. So I know on almost every single one of those pump jack applications, we have a line reactor, and we have also started providing some harmonic filters on in some spots and in some of those locations. So that is definitely something that should be measured more often, I would say, is harmonic content. But unfortunately, it's not necessarily the easiest or not necessarily the first thing that we bring our mind to say this might be the issue. But yeah, that's definitely I think that something that should be measured more often. So I actually had a conversation yesterday with an industrial company that's having some premature um, failures of some transformers. So when they're looking at harmonics, they're focusing on harmonics because on some of their distribution systems, they're using almost all of it is drives. So they're definitely focusing more on that than they previously were.
Gotcha. Okay, we got a couple more questions that have been coming in. Let's see, altitude derate. Is there an altitude? We talked about temperature specifications, voltage ratings. What about altitude rating?
Yeah, the general altitude D rate that we look at is 1,000 meters. So anything over 1,000 meters, which roughly converts into 3,300 feet, that's normally where an altitude D rate would apply. So normally we do 1% D rate for every 100 meters above 1,000. That's our standard D rate for altitude.
Yep. Another question. So sometimes not only are line reactors used for harmonic mitigation, but also for protection against transients. So maybe if you could highlight the topology of the front end, including some of those magnetics and what other components, like would we still recommend a line reactor to be used in conjunction with this product?
Yeah, so I'll reshare my screen here just so we can see what they're talking about. So this is the line reactor screen, right? So the line reactor schematic. So you see this part here. I'll turn my pointer on. So this part right here, that is the line reactor that we're talking about. So yeah, there's kind of a dual purpose for that, right? So it can help with harmonics, so reduce harmonics, and then also helps with any voltage transients because what happens is the voltage can come along this way, and then there's an extra device. It's almost like a transformer that it has to go through before it gets to the drive. So that's ultimately on a 6 pulse type of configuration. I think the question was more on the would we recommend a line reactor with a WC1? For harmonic mitigation, it's not needed. I don't think that's needed by any means, just because the harmonics are extremely less. For voltage transients, I think it has some plausibility. Yes, I don't know that I would recommend it for every single time. For certain applications, if you know that you have some bad voltage, that would be something to consider, definitely. You could also potentially consider like MOVs, like a different type of voltage protection device instead of a line reactor. So yeah, I think there are a couple components that could be thought to help protect voltage transients with the WC1.
Okay, and then another question, Terry, if you could kind of recover which communication protocols are included, most of those being IP or Ethernet based, and will the 485 versions of those protocols be available? You know, like backend MSTP.
Yeah. So here's the overall slide as well, or to begin with. And yes, so Modbus TCP and BACnet IP are built in. They're included. I believe the RS-45 versions are also going to be included as well. So the Modbus RTU and then also BACnet MSTP. So those will also be included with the WC1.
And so those won't be available at launch. So those will be later product enhancements,
Correct. Yep.
as well as Ethernet IP communications. for Rockwell PLCs as well.
Yep. Yep.
And looking through, Terry, I think that covers most of the questions that we received today.
Very good. Very good. So I appreciate everybody's time with us today. So thank you very much.